Swayam Prabha. Digital India. Educated India.
Good morning. I am Prashant Date from Mechanical Engineering Department at IIT Bombay. Today I will introduce to you the structural materials. Well, we take structural materials for granted. Normally speaking, the structural materials are there everywhere. In fact, we use structural materials like steels or any metals, for example, wood, composites, ceramics. So a wide variety of materials are used for a number of structures. The blackboard on which we write, the wooden paneling on the walls, the cement concrete walls, the roofing, the wooden benches, the all furniture made from metal and variety of other materials all form structural materials. So what is common among these? The commonality is certain amount of strength that is required. So basically structural materials always get loaded to some extent. So mechanical engineers always work with materials because when you try to make something, when you try to design something, you look at the structural strength of that particular material. You would like to have performance parameters in service taken into account at the time of designing, so that the material withstands the structural loads and performs to its full potential. So most products which we make are made from multiple structural materials. It's not just one structural material, but made from multiple structural materials. For example, take a bicycle. The bicycle, although is largely made from metallic materials, has got multiple metallic materials. That is one. So different grades of metals are used, and you have tires and seats which are made from non-metallic materials. So materials are generally are the means of obtaining desired properties of the product, and therefore we need to understand the property of every material and then match it with what is required. So every material has got certain properties, certain good things about it, and then we try to leverage the goodness of each material in order to get the final properties of the product. So every material contributes to some extent, or in some cases to a large extent, to the final behavior of the product in service. So when we try to shape the material, when you take a material and convert it into a final product, it undergoes a number of processes, and this processing is also an important feature of structural materials, because the structural material should withstand the material processing, the steps in material processing, and its properties should not deteriorate during the course of processing. Of course, in most cases we need to take care that the material properties do not deteriorate during the design of the process. So the design of the manufacturing process depends upon how the material behaves during manufacturing process. So you have different aspects of a material. One is therefore materials processing, as I just described to you, and the processing steps affect the performance. The basic properties of the material, the basic behavior of the material under the structural strength of the material comes from the chemical composition, and that chemical composition influences what is called as a microstructure. So, the microstructure is the source of strength. I mean, the loads whatever we put onto the structural material get transmitted to the microstructure, and this microstructure has got elements, features which impart the strength to the material to withstand those loads, and this strength comes in turn from the chemical composition. So, these are all interrelated terms, processing, composition and microstructure, they are all interrelated, because by processing you can manipulate the material of a certain composition to have a certain microstructure. You can alter the composition, you can alter the microstructure by changing the composition or by processing. So, there are if you take one say microstructure, you can change it by either processing or composition. Similarly, you can change the processing route depending on composition and microstructures. And then finally, the performance is something that is not changeable, that cannot be compromised, because performance is something that is a specification of the product which you are trying to make. So, you have three aspects to ensuring these things. One is the database about the chemical composition, the processing steps and the resultant performance. Then you have the computational, so that you do the computations to predict what will happen to a material of certain chemical composition when it is processed, and how a material processed in a particular way will perform in service. So, basically these are the three aspects. Experiment of course is the verification of the computation. So, computation is meant to get things first time right, meaning you do not want trial and error, you would like to compute the mechanical behavior of the material during processing and come to a final conclusion about how well it will perform in service. So, you have experiments, in fact you can even predict the microstructure, but then verify it using experiments about whether you are getting the right microstructure at the end of the day or not. So, with this you can shorten the processing time. So, if you take a material, a structural material, from material to the product in which the structural material can be used, you need the material of a particular chemical composition. You need to process it to impart the shape to it, so that you will be able to use it for a particular application. To give you an example, you take a table and a chair. You have, let us say, steel of a particular composition, then you process it, because the steel is not available in the form of a chair, it is available in the form of either sheets, plates, rods and things like that. So, you have to process that metal into a specific shape, and then the performance is expected in the form of sufficient strength as to give comfort to the person seated and satisfy the various specifications of being light, being portable and things like that. So, you have all three satisfying the requirements of the application. So, the objective of the course is to develop a basic understanding and broad overview of commonly used engineering materials, understand applications of naturally occurring as well as artificial materials, understand the tools and techniques to assess the effect of processing on the material, understand how desired properties are induced during processing, understand the correlation between design, material processing and properties induced in the product, and be able to interact with metallurgists and material scientists, because it is a very important part a mechanical engineer does, is to interact with material scientists, metallurgists, and it is important to be able to speak their language. So, it is also important to understand what they are saying and implement that in the job of the mechanical engineer. So, these are the objective of the course. So, basically everything is about understanding. So, this is not about developing any kind of expertise, but basically to understand what materials are all about. So, these are the course contents, and typically these are a few examples of materials in daily use. Of course, you will find hundreds of examples. So, what I would ask you to do is that you list out materials you encounter right from the time you get up in the morning to the time you go to bed, and you list out various activities you perform, the kinds of products you use during that period, and what kind of materials are involved during the course of that. For example, in the morning you get up, use a toothbrush. It is made of polymer or at times natural fiber if you are going to use if you use a dartan type of thing. So, it is like a natural fiber. Toothpaste is another material which is artificial material. Toothpaste tube is, so toothpaste is essentially not a structural but a functional material, because as you know, you would not choose a toothpaste, or you would not strive to impart strength to the paste. You would like to impart the functionality of cleaning your teeth. Toothpaste tube, however, is something that contains the toothpaste, and therefore it is made of structural material called as polymer. You have water tap, which can be made out of several metallic and non-metallic materials. So, you have a polymer if the cost is to be maintained low, or you have iron, steel, brass. Here you see a tap which is highly ornate. So, it is made of metal and it is made of brass. So, it would be much more expensive as compared to a polymer tap. So, the price of the product depends very significantly on the material you choose. So, it's the importance of this course is that you should be able to get the right kind of material, or choose the right kind of material from among the many alternatives which are available to you. Wash basin can be made from ceramic, or it can also be made from stainless steel. Supposing you are traveling and then in the trains you always find that the wash basins are of stainless steel. Similarly, in flights also the wash basins are stainless steel and never ceramic. Can you tell me why? Maybe you can write down this answer in a minute. You can stop the recording, write the answer in your notebook, and then restart the recording when you get back to the course. Okay. Teacups are available as ceramics, glass, polymer, paper, stainless steel, brass. Now, the variety of materials used are for different reasons. Like if you have, for example, paper, I mean, more and more new materials are being invented or used for this, because the tea can be had under different circumstances. For example, if it's a celebration, if the celebration has got some high profile celebration, then you would use a ceramic teacup, which is of course ornate. A glass teacup has got different aesthetic value, because supposing you are having green tea or something, it looks very nice if it is put in a glass teacup. Polymer and paper are used, we use for teacups at food stalls and things like that, where the functional part of it is important, namely that it should contain the tea and until you have finished drinking it, and it should be disposable. So, these are also structural materials. Polymer and paper are still structural materials, because you would like them to hold the amount of tea at a certain temperature, and therefore the structural properties here come into play. Stainless steel teacups are with so-called false bottom is often used in restaurants, where you would not let the temperature of the stainless steel cup rise, and so the outside of the cup remains cool, whereas inside you might have hot tea in it. So, stainless steel teacups are often used in restaurants and such establishments. And another brass teacup used to be used in the olden days, but nowadays it is not very common, but in the olden days in villages many times the brass teacups also would be used. So, there are many such examples which I have listed out, and these are not exhaustive of course, but this should help you start your thinking process. We use natural materials as well. So, we are increasingly trying to be environment friendly, and therefore we use natural materials as well. Now, all these materials, be it metallic materials, be it uh, ceramics, etc., they all are the outcome of the different elements in the periodic table. So, most of the metallic materials are elements here. So, when we talk about structural materials, structural strength is expected. So, materials occurring as gas under normal conditions like hydrogen, helium, they are not going to be of any use. Similarly, materials like argon, krypton, etc., all gaseous materials are not going to be of any use as far as our applications go. So, lithium, for example, is a talk of the town. Today we are talking about lithium ion batteries for electric mobility. Similarly, we are talking about sulfur, aluminium. So, there are all these are metals which have got very structural application. We make lots of things. For example, all aluminum car is something that we see. Audi A8 is an fully aluminum car. Similarly, we have titanium, aluminium, magnesium as materials being used in the aerospace sector because of their high strength to weight ratio. So, these are materials where the weight is small, the strength is high, and in the aerospace sector, it is important to have as light a structure as possible. So, the answer to my earlier question, of why do we find only stainless steel installations, whereas in many of our domestic applications we use ceramic installations. For example, the toilet fittings, wash basin for example, is of ceramic at home, but in a vehicle or in a mobile situation, be it flight, be it railways, you usually end up using a stainless steel wash basin or stainless steel toilet pan. So, there weight reduction is very important, and therefore, the bulky ceramic product is not used there. Instead, it is substituted with stainless steel. So, the selection of this material depends upon the strength to weight ratio. So, in a structural material, the strength to weight ratio is an extremely important parameter as far as the material goes, as far as application goes. And different sectors use different kinds of materials for their application. For example, copper would be used in the electrical and electronic industries. Copper is extensively used there for its electrical conductivity. Now, electrical conductivity is not a structural, so it is more of a functional material as far as electrical industries go. If copper is being used as, let us say, a means of storing something or of bearing certain load or bearing certain pressure, then it would be termed as a structural material. So, let me ask you whether paper as a material is a structural material or a functional material, because we write on paper, it is very common. For years we have been writing on paper, right. So, there we do not worry about the structural strength, we worry about the functional part of it, that ink should not spread, the paper should be of sufficiently large thickness. So, whatever you write should not lead to tearing of the paper, or it should not be seen from the other side as well. So, these are some of the considerations we use for paper, and we use it as a functional material. But then when you take a paper bag in which you would like to put your shopping, you do a lot of shopping and put your goods into it, then it has to withstand the load of the shopping which you have done, which means that the paper bag which is made of paper is essentially of a structural material. So, paper also has got a structural performance expected from it when it is being used as a bag. So, again the structural application is something that determines whether material is being used structurally or functionally. Similarly, you have properties like electronegativities. Now, these electronegativities are largely used in for functional uses, but then these electronegativities affect the performance of a structural material under different circumstances. For example, you make something out of steel, and then after many years you find that it is rusted at various locations. So, what is that? How did it rust? Why did it rust? It is because of attack of moisture and corrosive gases which are present in the air on the metal. So, degradation of the metal depends upon the service conditions under which it is operating, and therefore, the electronegativities of different elements are important, particularly because when you are using multi-material designs, you have materials of different electronegativities coming together, and therefore, this chemical attack will occur on one material more preferentially as compared to the other. And it becomes very important to understand this aspect while bringing in many materials together to form a product. So, it is not just the structural aspect of the product from use needs to be considered, but from durability point of view, to make sure that the product serves you for many years, it is important to have many other considerations like its corrosion resistance, its resistance to oxidation, and many other such things, resistance to, let us say, fatigue, for example. Fatigue is another thing which needs to be considered, meaning if you use something for many years, the metal itself gets fatigued, it gets tired out. So, that is the reason why we look for many attributes of a structural material. For example, we look at elasticity. What is elasticity? Elasticity is something that allows the material to deform a little bit and come back to its original shape. So, let us say you take this concrete wall, you push against it, you think that nothing has happened, however hard you might push, nothing is happening to the concrete wall. Actually, it would be deforming by such a small amount that you are not able to detect it with your naked eyes. You are not able to detect it unaided. So, you find that there is no change in the shape of the wall. You sit on the seat of a plastic stool or plastic chair, the deflection is detectable by a naked eye. So, the parts of the chair slightly deform, but then when you get up from the chair, it retrieves its original shape. So, this kind of property is called as elasticity. So, here there is no permanent change in shape, but there is a recovery of the elastic shape, recovery of the original shape when the person gets up or when the loading is removed from the product. So, the product, for example, you take any structural entity, there in use the deflection will be there, deformation will be there, the change in shape will be there, because you are loading everything to some extent, but it will come back to its original shape and size when the load is removed. So, that is what we call as elasticity. Contrast that with plasticity, where the change in shape is permanent, because what happens is initially when you are lightly loading something, it deforms and that deformation or the change in shape can be brought back, I mean that can be retrieved when the load is removed. But there are certain load levels, I mean this elastic deformation cannot go indefinitely. So, beyond a certain load, the material changes its shape permanently. So, at light loads there is a elastic change in shape, meaning temporary change in shape, but beyond that beyond a certain load, it will change its shape permanently, and then bringing it back to its original shape will become extremely difficult. So, the plasticity refers to a permanent change in shape. So, if you go on applying the load, then up to a point of plasticity, you will not, the structure will get deformed permanently. So, when we talk about the product being used, we do not want it to deform in a permanent manner, you want it to deform in a temporary manner to the extent possible, that is elastically. But when you are actually making the part, because none of your raw materials are available in the form of a chair, table, or a car, or railway coach or something like that. So they have to be shaped, they have to be deformed. So the raw material is available in a chunk of or block of material, block of metal, and that metal has to be deformed into that final shape. Now under those conditions you need to impart a permanent change in shape to the material so that it takes the shape you want, and then while in use it is much lightly loaded, while in use it does not change its shape at all. So this is something that we call as plasticity, which is required during the course of manufacturing. So you start with a form of raw material, let us say a sheet or a plate, and then you shape it into the body of a car. And so if the sheet were to deform elastically, it would again become flat after the load is deformed. So your purpose of shaping it to the body of a car would not happen at all. On the other hand, if you load it sufficiently so that it becomes plastic in nature, if it deforms permanently in nature, okay, then you need to apply sufficiently large load so that it does not retrieve its deformation, it stays in the deformed condition. So you take a flat sheet and apply sufficient load to it so that it takes the shape of the door or a bonnet or a boot lid or whatever you want, and stays there in a deformed condition. So the ability to withstand the deformation, change in shape, to what extent can you go on deforming? Yes, I want the material to deform and make it stay in a deformed condition. From manufacturing point of view, I want that, but then to what extent can I go on deforming? So this is a general term called as ductility. So malleability is an aspect of ductility where the material is malleable, meaning it can be flattened, it can be rolled to very thin foils. Now in electric batteries, for example, you need to have very thin foils which are needed for making electrodes of the electric batteries. So you need very high level of malleability in the material, and so copper and aluminum from which you can make thin foils of a few microns, say 20 microns, 40 micron thick foils can be made, and so you have a property called malleability, which is an important part here. Stiffness is again a structural strength. Yes, it's a structural strength. Brittleness is something that relates to the durability, because brittleness gives you an idea about how well the material performs against shock loading. So brittleness and toughness are the two properties which give you some response, give you an idea about response to the shock loading. For example, if something is brittle, it will withstand stress up to a certain point and then it will break. So there are two stages, either material exists or it doesn't. So there is nothing like plastic deformation, right? So brittleness and plasticity go one against the other. So brittleness is something where plasticity is lacking. So you have elastic loading of the material, light loading of the material, and if the material gets loaded too much, it will not yield, that is, it will not get permanently deformed as in case of metals, it will just fail, it will just break into two. So brittleness is something that where the transformation from an integral product to a broken product takes place instantaneously. Whereas toughness means you need to supply sufficiently large amount of energy before the product can break, which means that the ductile materials, malleable materials, they are able to take large amount of energy before they break into two. So they permanently change in shape as in plasticity. So you apply more and more load, more and more deformation to it, permanent deformation to it, but then it absorbs this so-called energy, and therefore it. So now, if you look at the Howrah Bridge, which is in Calcutta, it has crossed 100 years of its life, and it is made from a structural material which has made sure that it always deforms elastically, it has never permanently deformed, and then it has sufficient stiffness so that you are comfortable, because stiffness refers to deformation, elastic deformation under certain load. Yes, deformation is always elastic, but then if the deformation is too much, then you will not be comfortable using that bridge. So stiffness is a very important thing. And then you have this Howrah bridge made out of material that is corrosion resistant, because now you have the bridge exposed to the elements for years together, more than a century, and yet the bridge has not got corroded. So that is made from what is called as weathering steel, one variety of structural material called as weathering steel. Now you can find out the chemical composition through Google or from some resources or books. So with the abundance of structural materials, you have therefore lots of choices, and the desired properties can be taken into account and matched with the final product properties, and the material can be selected. So final selection of the material depends on the cost, because if you have a few candidate materials who satisfy the final objective of the product, then you would have most economically viable material selected, so that the product performs very well in the market. Now the new developments in the product call for new materials, new structural materials. For example, if you want to fly, I mean earlier people were not able to fly. Today flying is a very routine matter. But then as we go from let's say ground applications like automobile, where you use steel and lightweight materials, and then you are worried about only safety in crash, meaning you want occupants to be safe. In aerospace, you have to worry about high air speeds, frictional heating, high skin temperature. You know that the astronauts, many astronauts perished due to their spacecraft not being able to withstand the high temperature due to frictional heating during re-entry, because the re-entry shield, one of the tiles in the re-entry shield had fallen off during the takeoff, and therefore that frictional heating and high skin temperature becomes an extremely important consideration for material selection. Aircraft skin materials include fabric and wood. You can skin materials, see fabric and wood used to be used earlier, then it came to aluminum alloys, titanium alloys, polymer matrix composites, and so on. So there are many, there's a transition from some of the basic materials to, so earlier aircraft when they were made first time, particularly in Italy and by Wilbur and maybe Orville Wright and so on, they would have used fabric and wood, but then later on people started using aluminum alloys, titanium alloys, and then now people use polymer matrix composites or even metal matrix composites. So these are basically, composites are materials which are artificial materials, where we take into account different benefits of each of these variety of materials, be it metals and non-metals. So these are some of the naturally occurring materials. So these are, but then if you look at the composition of Earth's crust, different materials are available to different extents, and silver and gold being available at the availability being the least are the most precious materials. So the precious materials are the ones where which are least available. So we have seen already the applications of these metallic materials, and a bigger table, more detailed applications are given in this table. For I mean, you have beryllium, which are used for making molds, so that it gives large hardness as well as good thermal conductivity. And there are many other metals also which are of structural importance and very high strength to weight ratio. So here the strength to weight ratios are have been compared for a number of materials. So you have aluminum having this density, and you have a certain strength to weight ratio, and then you have composites, carbon epoxy composites having 1/6 of the value. So if you take metallic materials in the automotive industry, particularly the ones we see here, typically automobiles are made of steel, aluminum and lightweight materials, as we just saw, and these materials are not of just one single chemical composition. Now these are of different grades, and even in an automobile there are different functionalities to each one of these. So different criteria has to be satisfied by each one of these materials, and therefore even if you are using metal, it is not that the same chemical composition of metal is used everywhere. So be it the floor, be it the car body, the chemical compositions are going to be different. So different grades of material are developed, and materials are heat treated to different strength levels. So I would give you a task now to identify materials used in making different objects lying in your room, and make a table giving the name of the object and the material used to make it. Another set of materials is ceramics, and these are basically oxides, nitrides and carbides. So you have aluminum oxide, titanium oxide, titanium nitride, titanium carbide, tungsten carbide. So these are very well known hard materials, and these are used as abrasives and cutting tools. So you have these in grinding wheels and such tools. These are also used in the single point cutting tools. You have, let's say, boron carbide and some such some such materials being used as hard materials for cutting tools. Porcelain, cement and glass are used for general purpose. Glass is a functional material as well as structural material. If you are making a lens, for example, as in microscopes, glass would be a functional material because you are not leveraging the structural strength, but we are leveraging the optical properties of glass. So glass were used as a structural member for let's say absorbing the vibrations. For glazing, that is preventing noise, let us say, in VH type of applications, or double glazed windows is what we have. So these are the structural applications of glass, where the strength as well as the property of insulating property of glass is used. So basically you have ceramic materials which are stiff and strong, and they are inherently brittle. So they lack ductility, they cannot withstand impact, and therefore they break very easily. So impact can come from mechanical means, they can come from what is called as thermal shock, meaning you heat a ceramic and immediately cool it very rapidly, it will crack because of what is called as thermal shock. So these are kind of properties of ceramics, and the ceramics are usually insulating electrically as well as thermally, but you can have certain composition of ceramics which can be superconducting also. The 1, 2, 3 superconductors were essentially made from ceramics. Ceramics like ferrites have good magnetic properties as well. So if you look at temperature capabilities of structural materials, you have a wide range of temperature capabilities. You have different operational environment, and then time predicted excursions beyond usual magnitudes of impact or thermal shock. And then load of joining becomes very important, because you have many of these adhesives and solders which withstand very small amount of temperature, but ceramics, as you see, have withstand a wide range of temperature. Metals, so each of these structural materials have their own domains of application when it comes to temperature, and the behavior of these materials changes with increase in temperature. For example, metals would become much softer at high temperatures. Metals which were not ductile at room temperature would become more ductile at high temperatures. So these are some of the attributes of mechanical behavior of materials which are leveraged for structural applications. So now you can perform another task where you can find out materials which are resistant to oxidation when heated to high temperatures in air. So this also becomes another temperature capability, because these materials will give you which metal is resistant to rusting. For example, stainless steels are the ones which are made for withstanding high temperatures and not getting rusted, right? So there are many more materials. I mean, the stainless steel is a specific design composition of steel, but then there would be many more materials which are resistant to oxidation. There are some metals, interestingly, where oxides are volatile. They have very high melting points, but oxides are volatile. They just disappear. So if you subject the metal to high temperature and allow it to get oxidized, oxide itself disappears being volatile, and therefore the metal also disappears as an oxide. So there are very interesting properties of metals, different degrees of resistance to oxidation and different behavior of oxide at high temperature. So here are some material properties of the structural materials, because although you use the material for structural strength, you have inevitably some electrical and thermal conductivity also playing a role at in many applications, and therefore there is a comparison of the, not comparison, there is a list of materials where which are commonly used and their corresponding relative electrical and thermal conductivities, taking silver as a reference, because silver we know is a material of high electrical and thermal conductivity. So we have seen that many of these materials are used for different purposes. The ceramics particularly retain properties at high temperature. They are basically oxides and nitrides, carbides of different materials, and they have good corrosion resistance, thermal insulation, and relatively high strength to weight ratio at times. So typical properties of ceramics are given here. So again, if you were to design something, so the elastic modulus tells you the extent of deflection. So larger is the elastic modulus, lower is the deflection of the material under loading, elastic deflection of the material under loading. So basically you have, for example, Si3 and 4 would have a greater deflection under the same load as compared to BEO as seen here. So joining ceramics, because of their chemical nature, becomes an extremely important thing, because you cannot melt them, their melting points are too high. And if you were to join these, the oxidation, they are already oxides, so oxidation is not an issue, but then melting them is certainly an issue. So you have adhesives, you do brazing, and you do glass sealing as bonding methods under liquid phase. So it's not the ceramic that is in liquid phase, it is the adhesive, the brazing compound, and the glass sealing compound which is in a liquid phase. In solid phase, you have what is called a diffusion bonding, meaning you have two solid pieces put together, and the atomic species on the surface diffuse from one side to another. So you have two surfaces, two components coming together, and atoms from the surface of one diffuses into the other, forming a continuous bond. So electrostatic bonding and friction welding are two solid phase direct bonding methods. Now if you don't want to join using any of these techniques like diffusion bonding or friction welding, these involve a lot of temperature rise, by the way. So liquid phase would require a little bit, a small amount of temperature. Solid phase bonding requires a much higher rise in temperature, whereas mechanical arrangement requires no rise in temperature at all. So if you have a screw thread bolting and or shrink fit, so basically you join materials using elasticity of ceramics. So you use the elasticity of ceramics to good use, and then you have what is called a shrink fit. So the pressure between the joint between the two is generated by two elements coming together and one shrinking onto the other, so that the contact pressure between the two is maintained to a very high magnitude. Now composites are very artificial materials, they don't occur in nature. In fact, many of these carbon fibers, fiberglass, these are all artificial materials. Everything has to be made artificially. Glass itself is an artificial material. So glass cannot be mined from the mines, so you need to make it artificially. So you combine many of these materials, artificial materials, and then make composites out of it. So you have a number of strengths applications as a result of many strengths as shown over here, and there are many lacunae as well. So when you aim for certain strength, basically dictated by the application, there are areas where you cannot apply it, and that is why we need to identify the weaknesses as well. So you have many strengths as given here, and that makes it applicable under a wide variety of circumstances. However, there are word of caution here. For example, moisture absorption becomes a problem at high temperatures, and its degradation at high temperatures, and multiplicity of manufacturing defects which one has to guard against. So these are some of the weaknesses which one has to take into account. Already these composite components are being used. In fact, they are being used increasingly in the aerospace sector because of the need to make the aircraft lighter and increase its range. So you have doors, rudders, ailerons, spoilers, fairings, and so on. So Boeing 737, 757, so these are many models which we use or which we fly, and these are the ones where we are already using these composites. So the structure of the composites is shown in relative detail here. So you have aluminum alloy, polymer fiber, so layers of aluminum alloy alternating with polymer fibers. So this enables you to enhance the strength while making the overall composite much lighter. So the properties are maintained, but the weight is reduced. So again here the more details about composites being used in aerospace structures, and as you see, the use of composites has been increasing in the aircraft structures, the different parts of the aircraft, and the composite structures in a commercial plane are shown over here. So there are a significant number of structural applications for composites. Few more applications here, particularly in the engine components as well as in the military aircraft as well. So people want to make everything as light as possible and as strong as possible, and therefore wherever composites can possibly be used, they are replacing the metal. So the artificial materials are replacing the natural materials because of the combination of merit in individual materials and its application. So there is better matching between the application, the requirement of the application, and the constitution of the material. So earlier you used to depend upon what is naturally available and then try to match your application to that. But now you have an application requiring a big variety of properties which cannot be given by the natural materials, which are not available in natural materials, and therefore you have many artificial materials with a set of properties combined together to generate another artificial material which has exact match between the property you want and the property that is offered by the materials. So be it space, be it automotive applications, composites have been are coming in a big way, and the only issue there being, particularly in the automotive application, the repairability or the fatigue damage, the durability, and so on. So these are some of the issues which need to be assessed before one can deploy composites, and also safety. So here is some example of a car. So this is an electric car where they have eliminated metallic skin panels and used the composite skin panels. So they have reduced the weight very significantly, and the structural members of the chassis have been replaced by aluminum. Normally steel is used as structural member, but now they have replaced it by aluminum. So this way the entire weight of the vehicle has come down. So basically this is another view of the same car. So this is where they put the batteries, and therefore a lighter structure means much heavier batteries and more passengers to be carried. This is a crash structure ensuring safety of the vehicle. So here you have the crash, again a structural material where impact energy is absorbed by the structural material so as to protect the occupants in a frontal crash. So these are frontal crash structures. So similarly, Crash structures would be installed in doors also to prevent the occupants from getting injured in a side impact. So if somebody were to hit the vehicle from the side, the impact should get absorbed as well. So some of the one of the objective of this structural member here, which is made of aluminum, is also to absorb the side impact as well. So this is another view of the frontal crash structures and the structures there. Then we have glass fiber and so fiber reinforced plastics, polymers basically. So we have thermoplastics and thermosets as again artificial materials, and these are reinforced by different kinds of fibers, be it carbon fiber or glass fiber. Now glass fiber is used for, let's say, transmitting signals to a large distances. So these are so in that sense they are functional materials, but glass fibers used for structural application as shown here, the glass fibers are also structural materials. So we are leveraging the structural strength of glass to form members of a composite. Glass is a part of a composite. So glass cloth, for example, is a reinforcement in a polymer, so that you have the properties of the polymer enhanced significantly, and therefore the glass fiber, carbon fiber and natural fiber composites are coming in a big way so as to reduce the weight of the product. So everywhere we are trying to reduce the weight of the product and enhance its strength. But if you look at the energy required for this, these all artificial materials are energy intensive. So at the end of the day, you have to spend a lot of energy. So although you might save a lot of energy in use, because the product became light, you need less fuel, particularly in the transportation sector, you need less fuel. So you might say that emissions are reduced, but then overall, to make these composites, the significant amount of energy is required. So from that point of view, they are not all that green. But then yes, if you look at the strength to weight ratio, the enhancement of properties, yes, they are significant. Other fields, we have been looking at transportation sector related applications so far, but then there are many other areas in which these composites are applied. So you have skis, surfboards, etc., then tubular structures like tennis and badminton rackets, golf clubs, so sports equipment. Sheet structures are again used for many of these protective helmets and hulls of boats, etc. And there are big structures of varieties, climbing ropes, sword. For example, lift is the structural component of the lift, which actually withstand the load of the lift, makes the lift move up and down, is a rope. It's a rope of steel. So a steel wire is made into a rope. So similar to our coir ropes, that rope is made of steel, and that steel rope is able to take the very high load of the cage of the lift as well as with passengers inside. So typically you have 8 persons or 10 persons, and you have about 600-800 kilos of load to be taken into as a payload taken up by the lift. So the weight of the cage plus about 700 to 800 kilos of human load has to be withstood by the structural rope. So these are the ropes of high strength, which have to be very reliable, and so they are made from structural materials. So structural materials typically are steels in case of ropes which are used for lift. There are many so-called advanced materials which are able to withstand a big variety of in-service conditions. So you have high-tech applications, spacecraft, electronic equipment. Now electronic equipment would obviously require functional materials or employ functional materials, because functionality is what people are looking for. The strength that is required is to the extent of withstanding handling, conventional handling of these materials. But otherwise, you are not looking at the structural strength for their selection. The selection of the electronic material is based on its functionality or functioning behavior. So be it fiber optics, computers, and so on. So you have a big variety of advanced materials where you look for structural strength and deploy them. For instance, in this case, the body of the spacecraft, space shuttle, would be made of multiple materials. You have tiles which are meant for thermal protection, then composite propellant tanks which are supposed to hold the fuel at whatever pressure you might want to charge it in, and then you have titanium hot structures which are supposed to withstand very high temperature. So, as you see here, the strength, temperature behavior of carbon-carbon composites versus ceramic composites and many other composites are given, so that the merit of each is used depending upon the loading conditions. So, that is the advantage of using multi-material designs, where the material matches the in-service conditions and lives up to its property. So, well, one can argue that why not make everything of carbon-carbon composite, because anyway it is going to have strength irrespective of temperature. So, why not make it everything out of carbon-carbon composite, but then it is going to be too expensive. So, if you want to reduce the cost, then you need to also use many other cheaper materials, so that you do not use carbon-carbon composite for everything, even where it is not required. Similarly, shape memory alloys have the capability to reversibly change shapes. This is another variety of materials which is again a functional material, which has the ability to change shape with change in temperature. So, this is called as thermoelasticity, meaning as the temperature changes, the shape of the structure also changes. So, the growth in the structural materials, therefore, in the field of structural materials is taking place continuously because of, and it will take place in future also, because of special requirements that have driven the innovation in both materials and design, materials in processing. And the availability of these naturally occurring materials is very limited. The consumption can be much higher. For example, people are talking about limitations of lithium being used in batteries, because it is I mean, there is a time at which lithium will not be available. Soon we might consume the entire lot of lithium that is available. So, that is the reason why it is important to not rely on only natural materials. So, now how do you select the material, and which is, so at the end of the lecture I would ask you one question: which is now the best material? You have seen so many materials. You want application beverage container for carbonated beverages, and it requires CO2 it requires to withstand CO2 pressure, and it should be non-toxic, non-reacting, recyclable, aesthetic in shape. So, these are variety of attributes for the beverage can. So, beverage is what is going to be enjoyed, but then for it to be sold, its cost and aesthetic shape becomes an extremely important parameter. So, to end the lecture, I would ask you to make up your mind what material you would like to select for the beverage, and then I would also like you to pay attention to materials being seen at various levels. So, we have seen the macroscopic level, and then gone down. We will be going down to the microscopic level to find out why the strength comes in, who brings in the strength. So, we have seen that strength is under different service conditions, different temperatures, different a variety of situations, impact, thermal shock and so on. But then we need to understand what is the source of these properties, what is the internal source of these properties. So, I would like you to apply thought to some of the questions which have been raised during the lecture, and come back for the next talk, which will be on going back or going deeper into the source of how a strength is produced in the material, what really brings the strength into the material. So, we will see the different phases in the material. We will see the different phases which lead to the strength we obtain in the material. So, with this we close the first lecture. And if you have any questions, you are welcome. Thank you.